Okay, welcome to our next unit on vectors. We're going to start off with looking and describing, looking at some different definitions within the vectors spectrum. We're going to look at some real-life examples as well of what a vector is, because as it currently stands, you probably have no idea what vectors are. And in this lesson, all we're going to be looking at is knowing how to identify the difference between what's called a scalar quantity versus a vector quantity, and then being able to draw equivalent or opposite vectors. Okay, so we're going to keep things very basic for this first lesson, but let's just start really quick on some examples in the real world of vectors. So here's one example. I mean, if you've ever drawn on a sheet of paper an arrow, a line with an arrow pointing to something, what you've drawn was actually a vector and you didn't even know it. So a vector is anything that has both a magnitude, okay, as well as a direction. So it has some sort of quantity to it, as well as a direction pointing somewhere. All right. And so one of the major examples of vectors, if you end up taking a college program that deals with any sort of engineering or physics, you're probably going to be dealing quite a bit with vectors. Okay. So for example, if I were to open up this diagram, and this is a diagram of a ladder that is propped up up against a wall, and if you look at the diagram on the right, what you see is a series of forces that are acting on that ladder. Okay, so a series of forces. So you see that there's a force acting from the wall. Okay, from the wall, and actually, if I just take a quick screenshot, I can write here. So you can see that there is a force that props this ladder up against the wall, and that's called a normal force here. I mean, we don't have to get into specifics, but again, you can see that there's some sort of magnitude, there's some sort of force that's acting on this ladder in this position right here, and there's some sort of direction in which it's acting in. So in the case of the ladder against the wall, it's acting to the right, propping up or holding up that ladder. Same thing can be said about down here. This is also a vector. It contains a magnitude, a force of some sort, as well as a direction. And this force represents friction. So the friction with the ground is actually acting towards the left of this ladder, keeping it from slipping and falling, right? There is the force of this person's weight who is on the ladder, okay, acting straight down, as well as the force of the ladder itself, so the weight of the ladder itself, and the force of gravity as well, pushing down on the ladder. Okay, so that's an example. Oh, and there's another force here, another normal force, just like there was here, where the ground is actually holding up the ladder itself. Okay, so there's this idea of a magnitude and a direction. And if you take any sort of mechanical engineering program or course, along with many other engineering courses, you're probably going to be working with vectors or take a course that deals with vectors in some way, shape, or form. Okay, and so this unit just really serves to introduce that to you. Okay, so if I take another image, so if I go back here, okay. If we look at something like taking a basketball shot, okay. And this image is kind of blurry, but you may not even know it, but you're applying the concept of vectors even when you're throwing a basketball into a net, because you are throwing the basketball with some sort of velocity right, with some sort of speed, which is a magnitude, but then also direction, right? And so there's a force and a speed that's involved, and then a direction. And so once again, you don't realize it, but you're applying the concepts of vectors when you're trying to throw a basketball. And the same goes with in the programming of video games. Any sort of direction that the character in the video game is following, or whether there's an object that's flying through the air, maybe something that's thrown up and comes back down. That all has some complicated mathematics behind it, behind the scenes in the programming, that also deals with vectors, because there's some sort of magnitude and direction involved in all of that. Okay. Another example, okay, could be the tension of a stoplight being held up by two ropes, let's say, and those ropes are acting in some sort of direction, and there's some sort of tension force that is keeping that stoplight up. Okay, so same thing. So in particular, it really happens a lot with forces. Okay, and deciding, for example, if you're in engineering, deciding just how thick that cord or rope needs to be in order to hold up your stoplight, right? Because there's obviously a force acting down on those cords from the weight of the stoplight. And so you may need to calculate and decide how thick your cord needs to be and of what material and so on in order to keep that stoplight from falling. Okay. And lastly, okay, and sorry, that was the example of the video game. Okay, so just something being thrown. I mean, there has to be some sort of programming that goes on in the background of the proper force and direction that it takes for, in this case, the Angry Bird to go where you want it to go. Okay, so there's some pretty complicated math involved in that background programming of a video game. If we go back to our lesson, let's get into some definitions. Now that we kind of know the basics and we know that a vector has some sort of magnitude and direction, okay, that's exactly what the first definition here is, and I've already started this and written out the definitions just to save some time. Okay, so I've kind of already described this first definition of what a vector is. If we jump to specifically a scalar quantity and a vector quantity, let's start with a vector quantity. So a vector quantity is specifically something that would represent a vector. So I wrote out some examples. So it has to have both magnitude and direction. And a few examples of that is velocity. So there's a difference between velocity and speed. Okay, speed just, in the physics world, speed only indicates how fast you're going. It indicates just a magnitude. Whereas velocity in the physics world indicates that there is a magnitude, but also a direction in which you're going in. So there's a difference. There's a difference between the term velocity and speed, in case you didn't know. The same thing with displacement versus distance. You may think that they're the same thing, but I have definitions here of both that we're going to go over. Okay. Displacement is actually a vector quantity. So that means it must have magnitude and direction. Let's find out why. So it's a vector quantity that refers to, in quotations, how far out an object is. So it's the object's overall change in position. So how far away is it from some sort of starting position? Okay, how far out of place an object is. How far away from its starting position is it? So in that case, you're not only saying the magnitude, but you have to give direction. Okay, whereas in distance, it's strictly just a magnitude. It's what's known as a scalar quantity. Okay, it's a scalar quantity that refers to how much ground an object has covered during its motion. So it's strictly the magnitude of how far you've gone, and it has nothing to do with direction. That's what distance is, and that's known as a scalar quantity. Okay, so a scalar quantity is a magnitude with no direction stated. So it's strictly just a magnitude. And some examples of that is time, right? Time, you never give a direction. It's always just a value, a magnitude. Temperature. Distance, like I just mentioned. Speed, like I mentioned before that. Something like volume and mass. All of those items, all of those quantities, you're only giving magnitudes and you're not giving direction, right? And I think that makes sense. So if you state the mass of an object, you're not saying, in which direction that mass is acting in. You're only stating strictly just the mass of it, right? Whereas in a vector quantity, here's some examples of vector quantities. You have velocity, displacement, like we discussed, weight. So in the physics world, there's a difference between weight and mass, okay? Weight gives a direction as well as a magnitude. So it could be, say 30 kilograms going downwards, for example, going straight downwards. That would be considered weight, all right? So in the physics world, even though in your world you may think as weight and mass is the same thing, in the physics world there's a difference, okay? One is a scalar, one is a vector. Forces are a big, including gravity, the force of gravity. Those are big vector quantities that we're going to be dealing with a lot. Okay. Then you have what's known as equivalent vectors and opposite vectors. They're quite an easy concept to understand. Equivalent vectors, as you might have guessed, have the same magnitude and direction, right? Because they're equivalent. They might just have different positions. So, if I were to draw, if I were to quickly draw a vector, an equivalent vector would be the exact same magnitude and direction, but maybe just a different starting position, right? But that would still be considered an equivalent vector. Okay, whereas an opposite vector has the same magnitude, but the opposite direction. So if I were to draw a vector here, you would create the exact same magnitude, just in the complete opposite direction. Okay? So pretty easy concept to understand. I mean, it's kind of self-explanatory in the term itself of equivalent and opposite. Okay, now there's something we need to understand that's going to be discussed, or going to be a little skill throughout this unit that we need to really make sure that we're good with, is the idea of these directional, navigational angle definitions, okay? So there's something called a bearing angle, right? And a quadrant bearing. Now, everything we're used to so far is that all angles start, remember when we did our trig unit, all angles start on the positive x-axis, right? And they go counterclockwise this way. That's what we've been used to. But that's in kind of the math world. In the navigation real life application, that's not how angles are actually measured. Okay, they're measured using a bearing angle or a quadrant bearing. And I'm going to explain both, and we're going to do some practice questions for both. So a bearing angle is an angle measured clockwise from north and expressed as a 3-digit number. So clockwise from north. So if you ever see a bearing angle, suppose you see a bearing angle of, remember, it has to be a 3-digit number, 50 degrees. So if you have 50, you would have a 0 in front just to have the 3 digits there. So a bearing angle of 50 degrees starts on the north line and goes 50 degrees clockwise. Okay, so 50 degrees clockwise, probably somewhere there. So this would be 50 degrees. So that's kind of that's not what we're used to. We're used to starting angles on the positive x-axis. But if you see that there's a bearing angle being used, you have to know that it's being measured from the north clockwise. Okay? And it's a 3-digit number, even if there's only 2 digits that are relevant. Okay? You just put a 0 in front. A quadrant bearing is different. Okay, a quadrant bearing is an angle between 0 and 90 degrees. So it has to be between 0 and 90, whereas a bearing angle can be anywhere, from 0 to 360. So an angle between 0 and 90 measured from north or south to the east or west. So this is where we're talking about something like, let me show you an example. Something like, say, north, actually, let's go north 20 degrees west. So if you were to label here north, east, south, and west, okay, that's how this should be labeled here. North 20 degrees west that means that you start on the north line and you move 20 degrees west towards the west, right? Towards your W. So that there would be 20. Now you might get something like south 50 degrees east, right? In that case, you start on the south line and you go 50 degrees towards the east. Okay, so that's your location now, right? So remember that we're dealing with vectors. We're going to be getting direction. So we're going to be dealing with angles all throughout the unit. Okay, we're even going to be using some trigonometry as well. But we're going to be dealing with bearing and quadrant bearings, quadrant bearing angles throughout the unit. So we're going to get a chance to practice that below. But before we get to that, let's just take some time here to classify each quantity if it's a vector or a scalar after looking at our definitions. Force of gravity is a vector. Any sort of force is going to be a vector because it has to have direction. Gravity, we know, acts downwards, right? So it's a force that's acting downwards, which means it has direction. A weight of 9 newtons, I did tell you that weight is a vector, whereas mass is a scalar. Okay, so a weight of 9 newtons, now that weight needs to be acting in some sort of direction, right? Usually down, right? So if my weight, my body weight, okay, would be acting downwards, okay, pushing down on the ground that I'm standing on, okay? And then here we just have 12 kilometers. So that is simply a distance with no mention of any sort of direction. So this is called a scalar, okay? If this were displacement, there would be a distance magnitude, but also a direction, right? That would be called displacement. But in this case, we just have a distance, so it is a scalar. Another straightforward example is given a vector that is 200 meters per second on a bearing. So they're giving us a velocity, right, which is a vector. How do I know it's a velocity? Meters per second or units. Think of kilometers per hour. Well, meters per second are a type of unit that describes velocity. Okay, on a bearing of 130 degrees. Okay, so our first question here is to write a vector that is opposite to the given vector. Well, we obviously have to draw this vector here at a bearing of 130. Okay, so if I were to draw this at a bearing of 130, if my north line obviously is here, you start on the north line and you move clockwise from here. So this would be 90 degrees. Another 40 degrees would take us to 130. Okay, so we're down there in quadrant 4 here. Put your arrow, because it is a vector. And now what we're going to do, it says write a vector that is opposite to the given vector. No problem. So it's going to have the same magnitude, so make it the same length, okay? Just have it going in the opposite direction, right? So it could be something like this. Okay, it is the same magnitude. Let's assume that's the same magnitude, but it's going in the opposite direction. That's an opposite to the given vector. Now it says to write an equivalent vector, no problem. So let's once again put in our vector down here, 130 degrees, and that's my north line. If I were to draw an equivalent vector, okay, I can draw it with, it has to be the same magnitude and the same direction. So maybe it starts here. I can do that a little bit better. Okay, so same magnitude and direction there. That's equivalent. So pretty straightforward, right? That means it's got to have the same angle and it's got to be the same length of line. Okay. All right, so now let's get some practice with bearings and quadrant bearings, okay? So our diagram here, so we're given just one piece of information and it's our job. So this is one question, this is another question here, this is another question here, and then another question right there. So we're given, in each question, we're given one piece of information and then we have to decipher what the other two pieces are. So in this question, we're given a diagram and it's showing an angle of 48 degrees from the north there. So that means our bearing angle is simply 48 degrees with a 0 in front. It has to have 3 digits. Okay. Our quadrant bearing is going to say north, 48 degrees towards the east. Okay. So that's how you would state that as a quadrant bearing. Let's do number 2. Okay, let's do number 2. What is our bearing angle starting from the north line, going around? We go 90, 180 plus another 60. That means our bearing angle must be 240 degrees. Okay, 3 digits. Our quadrant bearing starts on the south line. It always starts north or south. In this case, it starts on the south, okay, because we're below the east-west line. South, 60 degrees towards the west. All right, pretty straightforward there. In the next two examples, we're given angles. So here we're given for number 3, we're given the quadrant bearing, south 15 east. And it's on us to draw a diagram. Okay, south, so start on the south, go 15 degrees towards the east, and there you have it. There's our diagram. What would the bearing angle be? Well, starting on the north, how far is it from here to here? It would be 180 minus 15, right? So 165 degrees is my bearing angle. Next, we've got to draw a diagram. Our bearing angle now is 300 degrees, which means we're starting on the north. Okay, start on the north, go 90, 180, 270, and then another 30 degrees to get to 300. So that in there is 30 degrees, right? And so all I did was I counted by 90s. I went 90, 180, 270, and then I know that to get to 300, I just need 30 more. What is this as a quadrant bearing? It starts on the north, goes this way. How many degrees did it move that way? Well, you know that everything in this quadrant should add up to 90. So if you do 90 degrees and subtract the 30, what you're left with is 60 degrees. So we actually started on the north line and went 60 degrees to the west. Okay, so there's some of these where you actually have to do some calculating, subtracting from 90 or 180 or 270, what have you, in order to figure out all the information that you need here. Okay, so that concludes our first lesson. We learned what a vector was. We learned some examples of vector quantities as well as scalar quantities. We were able to draw equivalent and opposite vectors, and we learned about quadrant bearings as well as bearing angles.